So here's our problem. So this is a airspeed versus ground speed problem. When planes are flying relative to the air. But the air is often moving, so their actual motion relative to the ground is what we call the ground speed. So they might be pointing themselves to the west, and they might be traveling with their engines acting as though they're moving 100 meters per second relative to the air, but with the wind blowing, that's blowing them off course. And so their actual path along the ground is different than their path against the air. We're being asked to figure out what the ground speed is. So this is a sum of vectors problem. We have to add the plane's speed to the air's speed, since the air is relative to the ground. And then ask ourselves, what is the plane's actual ground speed? What direction is it traveling? So this is our problem. Everybody understand the dynamics of the problem? All right. So, as always, I try to give you kind of a set of steps that'll help you kind of work your way through the problem. So, I'm going to write the steps over here that I think will be helpful. And step number 1 is you need to identify the given vectors. In the problem. So I want to preface this. I'm just telling you how to add vectors together. That's all this is. There's other kinds of problems that are harder, but this is what we have to do. So identify the given vectors in the problem. That's pretty straightforward for this one. So let's see if we can. I believe there are 2 vectors. There's the vector that describes the plane's airspeed, and there's the vector that describes the wind speed. So the plane is traveling 100 meters per second due west. This is the plane. And I'm going to write them next to each other, and you're going to see why in a minute. But the wind appears to be 25 meters per second, but it is 30 degrees east of north. All right, so I think we've identified the 2 vectors, kind of wrote them out in vector format. Am I going too fast? All right. Step 2. You want to create a coordinate system that you can apply in the same way to both vectors. Say both, but you can add as many vectors together as you need to in your problem. We won't do more than 2 or 3 because it's so tedious, but you could have a dozen displacement vectors You're trying to describe how you go from one place in Sickles to another. Just imagine every time you turn or change a direction or go up or down the stairs, how many different displacement vectors there are. Just going from here to the office, there might be a dozen, right? So when we talk about, how many vectors, you can add whatever number of vectors together as long as it makes sense for your problem. Now this part, there's stuff in this that you may not get. So let me be really clear. This is the part of the problem where you are applying positive and negative to your problem. Now, every problem we're going to have to establish positive and negative. And I'm making a big deal about this in every single unit, even though it doesn't feel like it's huge. It becomes huge suddenly when we start talking about things other than kinematics. So it's just a decision. You make this decision. You could flip a coin if you want. You just have to apply it the same way to every portion of your problem. So here we go. These are two-dimensional. So the first thing I'm going to do is come up with a coordinate system that is consistent for both. So I'm going to draw a little one of these because I think this is almost always easier if you have something to visually look at when you're doing this. You guys who tend to be, I don't want to use the word lazy, but it's probably the best word. You guys are trying to find the easiest way out of this. Believe it or not, drawing more helps a lot. And if you don't care, you don't care, but this helps a lot. So I want to apply a coordinate system the same to both vectors. So what I mean by that, I'm going to make this north and this one north for both. But it's more than that. That also means that I'm going to assign direction. So I'm going to make this positive and this positive for both vectors. And that makes this negative and negative. And I'm going to do that on both. I am consistently applying my coordinate system so that it makes sense and is applied uniformly to both vectors. We doing good so far? All right, back to our set of steps. As kind of a part B to this, we're going to be drawing a quick sketch of each vector so that step 3, break each vector down into its components. That vocabulary word again. Break each vector into its component vectors. This is the triangle problem. This is why we learned about the triangles. So I'm going to make a quick sketch. That's going to assist me in doing this. The plane, I don't know that I have to do very much work because it's 100 meters per second west. So that's my plane. 100 meters per second west. I really don't think I have to do a whole lot to break it up into its components, as 100 meters per second west is all in the x direction. Would you guys agree? So because it's all in the x direction, I'm just going to write negative 100 x hat plus 0 y hat. All right, not a whole lot to do there. I took it easy on you with the plane's, airspeed. But now the wind. The wind is 25 meters per second. Starting at the north, I turn 30 degrees towards the east. So my 30 degrees is here. I'm super careful about talking about this because I want to make sure that the angle ends up in the right place. The biggest mistake you guys make is not knowing where to put the angle. But you'll notice I'm reading it backwards. I'm starting from the north, turning towards the east, and then putting the angle in between where the north is and where my arrow is. Because I'm starting at the north. So this angle is relative to the north. So my angle measure has to always be attached to the starting direction. Now, I see an implied triangle. Do you see an implied triangle? That's what breaking it up into components is all about, is dealing with the implied triangle. So in this implied triangle, I see an adjacent side and an opposite side. That's my implied triangle. But these represent my component vectors. The adjacent side here and the opposite side here. My hypotenuse was given, it was 25 meters per second. So you guys, this might take you longer because you guys are still, learning this, or some of you never learned it. So I'm going to go through this in the most boring way possible because this is just what I taught you, the most boring way possible, but it works. I'm going to identify the angle of focus, 30 degrees. I'm going to label my triangle based on the angle of focus, opposite, adjacent, hypotenuse. I'm going to write out my trig functions. Sine 30 equals opposite over hypotenuse. Cosine 30 equals adjacent over hypotenuse. Tangent 30 equals opposite over adjacent. It seems like I can get the opposite side and the adjacent side from what's already written on the board. I don't really need tangent too much because that won't tell me very much. But sine is 0.5 and cosine of 30 is 0.866. And I just did it in the calculator. So now I'm going to find the opposite side, 12.5. Because half of 25 is 12.5. And now I'm going to find the adjacent side, 25 times 0.866. 21.65. I'm assuming you can do these things. But I've taken my vector and I've broken it up into its components. I've left out some of the math. This is the moment where if you don't know what to do, you speak up. Go ahead.
Can you show me how you got the opposite 12.5?
Sure. I'm going to solve for opposite here, where I have opposite over 25 equals 0.5. I'm going to multiply both sides by 25. That cancels out the 25 here, and I get opposite equals 25 times 0.5, which is 12.5. Good? Mm-hmm. And just do the same thing for the adjacent side. And you know where the 0.5 and the 0.866 came from, right? All righty. Feel good about that?
Mm-hmm.
You're welcome. All right, so shrink that back down. Looks like I can go ahead and write in the vector sentence for my wind speed. It looks like it's going to be 12.5 in the x direction, because it's pointing to the right, plus 21.65 in the y direction. All good? All right. Next step. We just did break each vector up into its component vectors. So step 4, add like components together to get our resultant vector. Okay? All righty. That part's pretty easy. I can kind of ignore all that stuff up there now. And I'm just going to take this guy, drop it right there, and add them up. All right, we're just adding the x ones together and adding the y ones together. So negative 100 and 12.5 will be negative 87.5 x hat. And 21.65 plus 0, so plus 21.65 y hat. This is our resultant. This is the ground speed of the airplane. We're not done because it's not being expressed as a magnitude and direction. But it is the actual answer. It's just that it's in rectangular form and not polar form. So my last step is to convert our answer to polar, meaning magnitude and direction. And those are the steps that are required to solve one of these problems, if all we're doing is adding. All right, so let's complete that last step. I find, since this is our answer, still better to use a few extra steps here. I think a sketch works good. So I'm going to make myself a quick sketch. I'm going to try and follow these directions because they're giving me directions on what to do. It says to go 87.5 in the negative x direction. And then 21.65 in the positive y direction. Remember, when adding components together, you add them tip to tail. You don't add them both from the center. And I'm going to go ahead and label 87.5 and 21.65. You'll notice I'm leaving the negative sign out because all it did was tell me what direction to draw that arrow. But now I want to draw in my resultant, which starts from the center and goes to the last vector. Now, do you see a clearly implied triangle here? Yeah, I know, I'm trying. They're not implied. It's like right freaking there, right? So our last step is to do the triangle stuff again. I'm going to use this angle as my angle of focus. I'm going to label this the hypotenuse, this the adjacent side, and this the opposite side. I'm going to say sine of my unknown angle equals opposite over hypotenuse, which is actually 21.65 over hypotenuse. I'm going to say cosine of my unknown angle equals 87.5 over hypotenuse. No help there. Tangent of my unknown angle equals 21.65 divided by 87.5. I think I can use that one to figure out the angle. So I will do that. I will fire up the old calculator and do inverse tangent of 21.65 divided by 87.5. Since somebody left me a fancy TI 84 plus CE, I can do it all right here. I don't know who left it, but they left it after the last test, and I charged the sucker up, and now it's mine. There's no name on it or nothing. Somebody will eventually ask, but they have not. So it looks to me like 14 degrees. It's actually 13.897 something. And if you're going to use this to figure out the hypotenuse, I would definitely use the longer number. So like I'm going to actually do that. I'm going to hit sine of my answer here. I guess I'm not going to. Sine of my answer. Yes, I am. Just do what I say. And I get 0.24019. So if I want to get the hypotenuse, I can say the hypotenuse equals 21.65 divided by 0.24019. And that gives me a hypotenuse of 90. Now, most of you know that you could have just found the hypotenuse by using the Pythagorean theorem. That works just as good. No reason not to. I'm just doing the trig stuff because we can. So this is 90. This is 14. Now, this is not the answer. This is only a part of the answer. To actually get the answer, you need to combine all the things to express it as a magnitude and a direction. So my magnitude is 90 meters per second. It was a velocity. You know, without units, you're losing a point. Put my little fancy thing here, and my angle is 14 degrees, but now I have to give reference. That 14 degrees starts from facing the west and turning to the north. So I am north of west. And that's it. That's this. And look, that was like 25 minutes for one problem. This is just a basic sum of vectors. I could have added any two vectors together and it'd be the same problem. Making it a plane isn't particularly interesting, except to think that if you're in the plane and the plane's going 100 meters per second, that doesn't tell you how long it's going to take you to get to your destination. You understand that this is relative to the air. So when they calculate how long it's going to take to get someplace, they want the speed relative to the ground. So that's how they determine how long it takes to get there. And you're assuming, of course, that the wind is the same everywhere, but it's not. It keeps changing. Worse, if the plane was pointed west and had to go west, would the plane arrive where it was supposed to go? I mean, do you see that it clearly wouldn't? That it's being pushed northward because of that wind. So there are, of course, the more complicated problems where we say the plane needs to be going west. What direction should it aim? So we are just barely looking at a little subset of what these problems are actually like. Do you guys get that? Because you probably know, if you have had any experience being in the water here in Florida, you know that you might want to swim towards somebody, but the current might have other ideas about that. So if you ever tried to cross a river, swim in a lake, been in the ocean, you know exactly what I'm talking about. So I just keep that. I meant to bring this up and I didn't. When you drew the triangle in with the green arrow, I immediately just chose this angle as my angle of focus. It seemed like the right thing to do. Well, the problem is that what I said to you before is you can choose any angle. And so you might be inclined to choose this angle. Why not? They both look about the same. Does it really matter? In this case, it kind of does. Once you've drawn that triangle out, always pick the angle that is near the center. And the reason is because that's the angle that's relative to west. It's against one of the directions. So when you're drawing them out, always choose the one towards the center because that's going to be the angle that is relative to north, south, east, or west. If you choose the other angle, you don't have anything to compare it to. Does that make sense to all of you? All right. Keep in mind that we're doing the most simplistic of problems here. So a boat is traveling at 25 meters per second due north, but there's a rip current. That is 60 degrees, 60 degrees west of south at 10 meters per second. What is the land speed of the boat? And direction. All right, so in a few minutes, I'll put answers here so you can kind of check your work as you go. But I won't put them up right away. I think you guys should kind of work at it a little bit. So good luck, and ask